Hello everyone and welcome to my channel. This is an educational channel. We look at all-encompassing theories of everything. We do deep dives into seeing what long periods of study on these different topics can yield. And today is our 424th video on the reciprocal system of theory from Dewey B. Larson. And Larson was an engineer in the 20th century. Around 1959, he proposed his two fundamental postulates about how the universe operated, and took those two postulates, just two sentences, and through a process of deduction, arrived at a theoretical universe. Basically, what his universe would look like if his postulates, or what the universe would look like if his postulates are correct. And then in many of his books, he compares his theoretical universe with the empirical universe of the scientific establishment that they had compiled in their tables and arrived at in their laboratories and observatories. We're looking at one of those books today, his book called Basic Properties of Matter. This is pretty much on chemistry, different aspects of atoms and molecules that have been measured, and Larson arrives at equations for these different properties, and then compares his results with the results that were published in the tables. And we are on chapter 3 here, called interatomic distances. He also studies other factors like the compressibility and the specific heat and the temperature relations, such as the melting point and the critical point. And eventually gets into electrical and magnetic phenomena. Also looks into isotopes and some other phenomena having to do with radioactivity. But here we're looking at interatomic distances. Now, the basics of Larson's reciprocal system of theory come from his two fundamental postulates, and the main postulate, the first one, is the one that we will focus on, which is that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with two reciprocal aspects, space and time. The upshot of all this is that, basically Larson is putting forward a universe made out of motion. In particular, Larson is referring to what he calls a scalar motion, which is a more generalized and non-localized motion that is bereft of direction. It's a motion that has a magnitude but has no direction. You can envision this with a balloon that you put dots on. As you blow up the balloon, all the dots are moving away from each other, but in no specific direction, or really every direction. Every location on that surface of the balloon is moving away from every other location. Then if you suck in the balloon, all of the dots and all of the locations will be moving toward each other. These are what Larson calls the progression, the outward movement, and the inward movement is analogous to gravitation. And that's what Larson calls a scalar motion. So Larson's universe is constructed upon this scalar motion. Now, if you're willing to accept Larson's, or even consider Larson's universe of motion, you have to be able to accept the fact that motion exists before anything moving. Motion is primary to the thing that's moving. And in fact, the thing that's moving is actually motion. Matter is just another form of motion. Also, in order to deal with the reciprocal system, you have to conceive of motion as in Larson's the reason why he got the term reciprocal system is because in Larson's estimation, motion is the relationship between space and time. And this sets up a generalized reciprocal relationship between space and time. Motion is basically a fraction with space or time as the numerator and time or space as the denominator. In the most simple case of speed, such as the car is moving 20 miles per hour, 20 miles of space in 1 hour of time. Space over time equals speed. And you can see a reciprocal relationship if you try to multiply the speed by 2. Now you can say the car is now moving 40 miles per hour. Or equivalently, you can say the car is now moving 20 miles per half hour. You can either multiply the space or you can divide the time by 2. They both give you the same result. That is a reciprocal relationship. Now, what you have to be able to accept is that, for thousands of years, we've looked upon our universe as being kind of a drama that's going on the stage or in the setting of space and time. 3 dimensions of space and moving through time. And that is, kind of the stage upon which we act. But in Larson's universe, space and time are not the container of the universe like that. They are, in fact, the contents of the universe. The universe is made out of space and time. So that's another adjustment that you have to make. Then, you've got this scalar motion. Larson calls that clock time and clock space. The clock is always getting later and later and later, or farther and farther and farther apart. Space is always getting farther and farther and farther apart. Those are the scalar clock time and clock space. If you abstract the universe, you get what he calls coordinate time and coordinate space. This is really like Euclidean geometry, X, Y, Z coordinates in a still frame. This is what we observe in the material sector, in the place that we reside in the universe. We observe coordinate space, 3 dimensions of space in a still frame. That's why we see a setting of space and time. 3 dimensions of space in a still frame, and clock time, always moving forward or progressing. And that is, an abstraction. That's really what we get when we basically stop the universe, when we assign a reference point, where we assume that one portion of the universe is motionless. Just in the same way of that expanding balloon, we identify one of the dots on the surface of that expanding balloon to be motionless. And then when we do that, then we can finally determine the directions that are involved in, the other dots, because we're taking away the motion from the one dot that we've assigned arbitrarily to be the reference point. Now, the other important aspect is the discrete unit postulate. Space, time, and motion come only in discrete units. They are quantized. You have to have a full unit before you have anything. So, you have to have a full unit of space before you have space, and vice versa with time. And if you have exactly 1 unit of space in 1 unit of time, space over time being speed, 1 unit of space and 1 unit of time, you have what Larson calls unit speed, which is also known as the speed of light. So the speed of light is 1 over 1 equals 1, unit speed. And this is the background motion of the universe, or the ether of Larson's universe. The origin, what he calls the progression of the natural reference system, is a motion outward at the speed of light in all directions. This is the progression of the natural reference system. So this is the system, the reference system that the universe actually conforms to. So when Larson makes his measurements, he measures from that 0 point, so-called 0 point. Unlike legacy science, which measures from zero motion from where we see it, from our standpoint in coordinate space and clock time. So in Larson's universe, basically half the universe is moving faster than the speed of light, and half is moving slower. The half that's moving slower is called the material sector, and that's what we're familiar with the coordinate space and the clock time. But if we move across that boundary, the roles of space and time reverse. And if we're over in the cosmic sector, where the speed of light, where everything is faster than the speed of light, then we are in the realm of coordinate time and clock space. 3 dimensions of time in a still frame, and space is always getting farther and farther and farther apart, the progression or the flow of space. So these 2 sectors of the universe are more or less reciprocals of one another. And then within each one of those sectors, the material and cosmic sectors, we have also an inside region of each that Larson calls the time region and the space region. The time region is within the material sector, and this is again part of the discrete unit postulate. If you don't have a full unit of space, so like if the interactions are occurring in less than 1 unit of space, which is common for atoms and molecules to be interacting in less than 1 unit of space, then you don't have space, because you have to have a full unit. So if you don't have space, then you have to have time, because space and time are the contents of the universe. It's got to be one or the other or both. And so if it's not space, it's got to be time. Larson calls that the time region. Now, when you cross that unit of space and enter the time region, you again have to switch the rules. And now the progression of the natural reference system is moving inward, and gravitation is moving outward. And the same is true over in the cosmic sector, where you have interactions in less than 1 unit of time. Then that corresponds to what he calls cosmic atoms and cosmic particles and cosmic compounds. And but you don't have time, because you have to have a full unit, so you only have space. And he calls that the space region. And in the space region, the rules again reverse, and the progression is moving inward, and gravitation is moving outward. Now, in this chapter here, we're talking about the interatomic distances in compounds. And the interatomic distance is established. Again, he mentioned here just in the last episode how the interatomic distance is the distance between atoms and molecules. It is not the size of the atoms and molecules. It is the distance between them. And this is established in the solid state like a crystal structure. It is established in the time region for a material atom, and it is established at an equilibrium where the progression and gravitation are equal. Now, the progression is a constant. It is always outward at the speed of light in all directions. Within the time region, it is inward at that speed in all directions. Gravitation is variable based on the inverse square law. You know, the closer things are together, their attraction is based on an inverse square. So it is a kind of an accelerating function or second degree function. So we have to establish the place where those two forces are equal. They're not really forces, what Larson calls as-if forces, because they only attain a force field, or as a result of assigning a reference point and then being able to determine a direction. But they behave exactly as if they are forces. Okay, we'll let Larson take over here and see if we can make heads or tails of what he's saying here. You know, he's kind of getting into a lot of details that we haven't covered, especially in this episode. I will try to clear up any confusion, but sometimes it's difficult if I'm confused myself to clear up any type of confusion. We'll see how it goes. You know, I have to emphasize again, this is like detective work. You know, you have to just kind of read it over and glean whatever you can from it and store it away. And whatever questions you have, store them away, and they probably will be answered at a later point. You know, you can't get on Larson for his writing because he's attempting to articulate things that have never been articulated before. He's having to arrive at a new language for things, and it's just not that easy. And so he can be criticized, you know, ad nauseum if you want to. But if you just look at the task that he put in front of him, the fact that he managed to do anything at all is what we should be grateful for. Okay. Closely associated with this cubic diamond-like zinc sulfide class, which he just went over in the last table, the zinc sulfide class, which is, well, I guess zinc is 30 and sulfur is 16, so I'm not sure. I thought we were talking about, sorry to backtrack here. I thought we were talking about the sodium dioxide class, or disodium oxide class. I don't see zinc in here at all, so I'm a little bit confused about that already. That we haven't even started yet, but let's just keep going. Closely associated with this cubic diamond-like zinc sulfide class of crystals is a hexagonal structure based on the same orientation and containing the same equal proportions of the two constituents. Since these controlling factors are identical in the two forms, the crystals of the hexagonal zinc oxide class have the same interatomic distances as the corresponding zinc sulfide structures. Well, you would think so, since they are lined up on the periodic table the same way, but in such instances where the interatomic forces are the same, there is little or no probability advantage of one type of crystal over the other, and either may be formed under appropriate conditions. Table 9 lists the interatomic distances for some common crystals in these two classes. I'm just moving up here to make sure that He didn't skip anything. I don't remember him talking about this zinc sulfide. Um, Here we go. Maybe let me just read the paragraph before this, before we get into this table. Another type of orientation that forms a relatively simple binary compound is the rotational combination that we found in the diamond structure, as in the, not diamond such as carbon, but diamond shape structure. As in the elements, this is an equilibrium between an atom of division 4 element and one of division 3. The requirement being that when you add the two valences, you get 8, I think. And obviously, the only elements that can meet this requirement by themselves are those whose negative rotational displacement or valence is 4. But any division 4 element can establish an equilibrium of this kind with an appropriate division 3 element. Okay, he doesn't mention zinc sulfide there, but okay, now we're on the table. And here he presents various elements and their calculated interatomic distances. He also presents the specific rotations. Now, the specific rotations those are the components of all of his elements and his elements. The elements are the periodic table, where the periodic table just uses one number. Larson uses 3 different numbers. The first 2 are 2-dimensional rotations, and the third is a 1-dimensional rotation in opposition. The two-dimensional rotations occur alternatively, and you really have to, in order to nullify the progression, you have to have a rotation just to nullify the progression. So, and the progression has to be nullified in 3 dimensions before it gravitates. So even the lowest atoms, such as hydrogen and helium, they have helium has a three number notation as 2, 1, 0. 2 primary 2-dimensional rotations, or he calls them magnetic rotations. 1 secondary 2-dimensional rotations, and then 0 electrical rotations. 0, if it has 0 in the electric rotation, that means it's on the noble gas series, and it has like no valence there. It's an inert gas. And so, for example, hydrogen, its numbers are 2, 1, negative 1. And when he makes these calculations, he uses specific rotation, which means, I believe, that he adds 1 to one or more of these first 2 numbers. And I'm still kind of confused why he uses, for his specific rotations, in a lot of cases he uses 10 or 5 as the neutral. And then I can understand that for a valence of 4 or a valence of 8, which is, what we're dealing with in a lot of cases. But, okay, so he goes through various compounds here. He's got aluminum, phosphorus, I don't know what that's called, but he calculates that at 2.32, which is in angstroms, observed at 2.35. Aluminum, I think that's AS is astatine or something, and calculates that at 2.62, and the observed is way down at 2.43. So that is a measurement that's very far off. That's about the furthest off that I've seen so far. He moves on. We've got copper chloride, copper bromide. Making these calculations. Here he's got one that's exact, 2.46 for copper bromide. And then he gets the zinc sulfide. 2.36 is the observed. 2.32 is his calculated. Zinc selenide, 2.46, observed at 2.45. We've got gallium phosphate, I guess, or phosphide, I'm not sure. 2.32, measured at 2.36. Here we got silver iodide, 2.80, calculated at 2.81. I don't see any other ones where he's off by more than 1 or 2%. So it looks like there's just that one that's off. The comments that were made about the consistency of the specific rotation values in Table 7 and 8 are applicable to the values in Table 9 as well. That's what we just looked at, Table 9. Most of the elements participating in the compounds of this table have the same specific rotations as in the previous tabulations, and where there are exceptions, the deviations are of a regular and predictable nature. A feature of Table 9 is the appearance of one of the normally electropositive elements of group 2b, aluminum, in the role of a division 3 element. If you don't know, the division 2 elements are really on the left side of the periodic table with a valence of greater than 4, or 4 or greater. And then division 3 are on the right-hand side of the periodic table, electronegatives that have a valence of 4 or greater. Division 1 is electropositive, valence 4 or less. And division 4 is electronegatives, division 4, valence 4 or less. Beryllium and magnesium also form zinc sulfide type compounds, but like the lithium compounds previously mentioned, they are irregular, probably for the same reason, and have not been included in the tabulation. The division 3 behavior of these normally division 1 elements, like aluminum, is a result of the small size of the lower groups. Groups 1 and 2, groups 2 and 3, I'm not sure what. Aluminum would be in group 3, I believe, and those groups are only 8 elements long. Aluminum is in the group between neon and argon, and so that's only 8 elements. So really, there's a redundancy there, between the division, certainly between division 1 and division 2, and then division 3 and division 4. But he's even putting the redundancy between division 2 and division 3. So the small size of the lower groups, which puts their division 1 elements into the same positions with respect to the electronegative 0 point as the division 3 elements of the larger groups. This relationship is indicated in the following tabulation, where the asterisks identify those elements that are normally in division 1. So he lists division 3 elements here, and they include beryllium, boron, aluminum, and magnesium, which are normally in division 1. And then he lists those along with copper, silicon, germanium, nitrogen, phosphorus. I forget what AS is. Oxygen, sulfur, selenium, fluorine, chlorine, and bromine, and zinc. None of the orientations thus far considered is applicable to compounds of the division 2 elements. The normal orientation does not exist above a specific rotation of 5, as the higher value would put the relative rotation above the limiting value 10. The zinc oxide and zinc sulfide type of combination are electronegative structures, and the reverse orientation of the division 2 elemental structures is not available for compounds with negative elements. The division 2 elements therefore form their compounds on the basis of the magnetic orientation. This type of structure is theoretically available for any element, but its use is limited by probability considerations. It is utilized in many of the compounds of division 3 and division 4, especially in the higher rotational groups, but rarely appears in division 1 combinations because of the very high probability of the normal orientation in this division. And recall that, Larson uses probability, in his derivation, in his deductive development. What is the most probable? Following the principle of plenitude, what can exist does exist. Since the magnetic rotation is distributed over all 3 dimensions, its effective component is not altered by a change in position and has the same value in the magnetic orientations as in the corresponding compounds based on the electric orientations. In order to establish the magnetic type of equilibrium, however, the axis of the negative electric rotation has to be parallel to that of one of the magnetic rotations, and it is therefore perpendicular to the axis of positive electric rotation. Consequently, the latter takes no part in the normal interatomic force equilibrium, and it constitutes an additional orienting influence, the effects of which were discussed in Volume 1, Nothing But Motion. In these compounds of the magnetic type, the displacement of the negative component, negative x, is balanced by a numerically equal positive displacement. Okay, we're going to just stop right there and probably backtrack a little bit tomorrow to get started. But just hang in there. Some of this might seem gibberish, but just get to what you can. Thanks. Have a great day.